The topic of my talk is object-oriented embedded hardware for operational excellence using AI. I didn't put the AI part here. Well, I guess AI kind of attracts people. But anyway, so what I'm going to talk in the next 30 minutes is our approach to embedded hardware design. So embedded hardware is obviously not just the hardware side, there's also software side as well. So, but we're not talking about object-oriented programming, for embedded design. We're also not talking about high-level synthesis tool, like, you create your objects and you try to map them to the hardware. Although some people do that. We are talking about developing embedded hardware using domain-specific languages like System RDL and PSS and some other additional technology that we have. So the point about this talk is like how you can organize your teams and your projects so that there is less loss of information, there's less bugs, a faster time to market, all of that by changing the methodology. And let's see. So start with a typical embedded system where you have CPU, multiple CPUs connected to various programmable IPs on the peripheral. Maybe there are bridges. There is a interconnect fabric. All these are being accessed by the CPUs, and on the other side, you program the CPU through C, C++. So that's what we're talking about. And on this side, we have the sensors for bringing in information from the outside world. So that's my typical embedded system that I'm talking about. If you look at the system in another way, I call it the onion. It's not a new thing, but basically at the top you have the application software. You dig in, you have the software driver. If you go below that, the software driver uses the bus connection layer. There's those buses, the register buses, and then there is the register IP layer, where you have all the registers, the programmability part of the embedded hardware. And beyond that, there's the hardware layer. That's where your application is. So let's dig deeper into this. So the register bus layer is really any register bus like AMBA, AXI, AHB, APB, TileLink, Avalon, proprietary. People have systems have a wide variety of these buses. And then you could have different bus architectures. You could have different layout. You could have different blocks inside blocks, and you could have a deep hierarchy. Then there are aggregation logic, where you have the bus coming in and you have decoders and you're talking to all these specific blocks, the client IPs that I showed you earlier. You have multi-master arbiters, you might have a NOC. So all this variability is there in this register bus layer. So this is like a typical, just high-level view of that bus topology. So you have the processor 1 and 2, and then you're trying to talk to all these slaves or let's say targets, and going through the decoder hierarchy. So basically, in the IP, you have all these registers. The complexity there is there can be a wide variety of these registers. Interrupts, arrays, counters, locking register, shadow, trigger buffer, atomic registers, indirect registers. There's a whole litmus of these registers. Different accesses of those registers as well. So registers are the thing that the software or the CPU looks at. The CPU has these transactions to these registers. And they play a significant role in the design of the embedded hardware. And it's very important to manage it properly. And there are industry standards like System RDL and IP-exact, to name a few, in this space. Again, they're basically describing these registers and so that you can generate things from it. So when you look at these, like just a closer look at the architecture, you have these register buses. These blocks might be talking to each other, but the CPU is talking to these blocks through these registers. So the System RDL language, how many people here know about System RDL? Raise your hands. You guys know about System RDL? No? So it's a language to describe these registers. It's not a very new language, but there was a recent 2.0 that came out a couple of years ago. So that language is used to describe these registers and memory and the register map and all the attributes and behavior, not necessarily too much about the behavior, but all the attributes about it. But you can extend it with UDPs and add behavior to it. Like, for example, the type of registers I showed, some of them, like interrupts and counters, are intrinsically part of the System RDL, but others, you can add UDPs, user-defined properties, and you can add additional behavior to them. The idea is to capture in a declarative manner the interface that the software sees of the hardware. And so this is basically used to people have their own implementation, or you can get commercial solutions where you can take these System RDL description and generate RTL from it. And this is just a little bit more detailed view of the register, how it looks. Basically, you describe address map is at the top. You got several address maps. Each block is mapped to an address map, and you can have an address map inside an address map. You can have a register file. Then you can have, of course, you have registers, and you have fields inside the registers. So pretty logical way of looking at it. And then you have a memory construct as well. And you can describe how the CPU looks at it. That's the SW property, the software, how the software looks at the register, and HW property, which is how the rest of the hardware looks at that register. So you can have, maybe there are about 30 odd access types from the software side, like write to clear, write to toggle, or read to clear, so on. So you can have all those properties described here. And from the hardware side, there are additional ways like read or write, or read write, or maybe there's no access from the hardware side. So all those things, you can declare them in the System RDL file and then generate your code from it. Other than that, there is the address, and like I said, there are other properties. Like, for example, reg width is one of the properties here. So beyond, if you look at that over here, well, the stack that we're working on, we looked at the register bus and the registers. Now the hardware application, like your embedded hardware application, it's not just the registers. Obviously, you're going to do something with them. So these are like the actual functionality. This could be the FSM. You might have an FSM there. You might have data path. Maybe other glue logic. So you describe these as well. That's the application layer. That's where your secret sauce is, right? And now going back up to the hardware-software interface, the hardware-software interface has the register map, which is basically the memory map and interrupts, including the ISRs, the interrupt service routines. That's the interaction between the hardware and the software. But that's only the storage part. There's also the register sequences. How are these registers accessed? Or say, for example, you're programming something. You will have to program these registers in a certain way. I'll give an example later on. But the point here, the hardware-software interface layer has a storage, which is the registers or register files, and then there are sequences that act on those. Those are like methods. So this is the kind of, this is why I said this was object-oriented, because in object-oriented you have storage, right, the variables, and then you have methods that go with it. So similarly, you can look at the hardware in this way, that there are these registers, and then there are register sequences. Now, to describe these register sequences, we have a GUI in our tool iDesign Spec where you can capture these sequences. Then also you can use PSS. So PSS is a new language. Okay, the next slide. The PSS language is again a very recent innovation. Actually, now it's onto 3.0. Actually, again, that's part of Accelera. You can use it. Mostly it was designed for testing the hardware, like for multi-core hardware. Well, we're using it for programming it, like at the IP level. So the language is pretty elaborate. It has like a modeling layer and a realization layer. Has anybody heard of PSS here? No? Yeah, a little bit? Okay. So it's new, and and the Accelera and people like our company, Agnisys, which is trying to promote it, we're trying to popularize it, so people start using it, describing their test intent in this language. So the modeling layer is where you capture all the high-level intent of what you want to do. And the realization layer is where it actually converts that intent into actual programming. It will do the scheduling, and it will manage the resources and all that. So we're using it as we're taking a subset of the PSS and describing how you are accessing these registers, like how you're initializing the hardware as a unit. So here's a little bit more detail about just like what it looks like. Just you have the bit fields over there. And then here you're saying don't worry about the syntax. Actually, I'll show you another view of this thing which has less of this complexity. I mean, it looks more complex, it's not that complex. All I'm doing is like describing a register, and then there's a bit fields, and then I'm programming it in a certain way. And this could be procedural, means I can have controls, if then else, or loops and stuff like that in here. So this is the PSS register model. And then the PSS register sequences, once again, don't worry about the syntax. Basically, I'm saying how to program it, how to do a read and write, or how do I initialize certain thing. I can share the slides with you if you want later, so you don't have to take pictures. If you want to take picture, please do, but sure. So this is where you will capture the intent. You will capture the programming of that hardware. So remember, the registers are the storage, and the sequences are the methods that go on top of that. And so now, if you go, you look at the software layer, which is the device driver, OS, and application. The OS is not required for all applications. You you don't need the OS. On top of the embedded hardware, you could just directly run bare metal, but sometimes you need the OS for, like, maybe you need additional capability, like, for example, like file system, or you have a real-time OS, where you need to be very specific about the time you respond to certain. You got multi-threading and those type of things. So that is OS, but then you can do the testing directly on the hardware-software interface, right? Here are some of the examples of the OS. Linux is an example, but so are all these. And then you have Ziffer, which is a pretty popular up-and-coming OS. Then you have the device driver. So now the device drivers are, how the software sees it. It's the interface between the hardware and basically it's a high-level view of the hardware that the software sees. So so the device driver provide a standardized interface for software application and really shielding the software people from all the intricacies of the hardware. So the way it shields it is by, if you were to describe these sequences, then the software people don't have to see it. They just call a function, and they don't have to look at all the gory details of the registers and other stuff there. So it provides an abstraction and uniform interface, initialization and configuration of devices, and manages the transfer. So device drivers are very critical. It is very tedious to create device drivers. I don't know are there any people here doing device driver work? Yeah? Do you agree? Yes. So, and the reason is, like, the spec is not clear. You don't know how the hardware person designed it, how it's supposed to work. So it's always time-consuming, error-prone, and it's just there has to be a better way to do it. So that's what we're proposing here is, like, you design your hardware with those methods. So those can be the building blocks for your device driver people. So save them some gray hair. So then we go to the software layer on top of the OS. Basically, this is just an example of the application layer. So this is basically calling the device drivers or the kernel, the subsystem, and which is talking to the hardware. This is from the Linux kernel development. In order to have an object-oriented view, you have to start early from the ground up, right? So here is an example. I just took this from the net. Basically, it's a RF transceiver from TI, and I opened the spec, and here is the programming of how do you get the frequency? How do you program the frequency that you want it to operate at? So now you can read it, all this. There is some lookup tables and all the equations. And guess, if you have a software that deals with this, who's going to do this programming? It's the device driver. And how does it do it? It looks at the registers. And remember, it goes through all that chain of the stack of things that I showed you there, right? So we basically took that and put that in system RDL. So that's it's a snippet. It's a long description. There were like hundreds of these registers. So we captured that in system RDL. Here is the frequency 0, 1, 2. So they have 3 registers, only 8-bit registers in it. So you have to take that big frequency number and divide it into 3 parts. So here is our software. So here we are describing one of the equations that you saw earlier, this one, and describing it in our tool, in the iDesign spec tool, basically capturing the sequence of programming it. So don't worry about the details, I'll show you the slides with you, but basically the same equation is captured here. So you captured the registers and you captured how you're programming it. And now this this becomes the building block for others. So for example, here I'm programming those registers. I'm calling individual register fields, and I'm updating them with the values here. I'll let you take a look at that. But it's also calling the RF evaluate frequency setting, which was defined earlier. So you are not only building the register interface, you're also capturing the methods to program it. And from that, so that was this is one way of doing it. The other way, this is a GUI way of doing it, or maybe you can say spreadsheet way of doing it. This is part of our tool. The other way is the PSS. You can capture that same information in PSS as well. So that's an industry standard, so you could do that as well. So one is a GUI, one is a non-GUI, and the same methods are here. And then from that, now we can generate the C output, for example. We can generate a whole lot of things. Now that you've captured it, we can generate a whole lot of things. And that saves time for a lot of people. Like the C output is generated. There's the C output. Header files are generated. UVM for verification is generated. Then we can also generate tests from that. Because you've captured the registers, you captured the sequences, we can test those as well. Again, this is UVM. Because you've captured it in a high level form, we can translate that into all these languages like System Verilog or C or others. We also generate a programmer's reference manual now. Now that so the registers are here, all the frequency 0, 1, 2, whatever. Those are all the registers. And then a programmer's reference manual, the sequence view, which is like showing the graphical representation of how the programming happens. Right? So I think that's the whole point about this, is that a single source, single golden specification to basically generate all collateral from it, and no duplicate work, enables reuse, and that's how it is helping your team produce faster. Faster time to market, easier debug, high quality, no wasted time. Imagine doing all this by hand every time. Somebody makes a change in the design, you have to go through all outputs need to be changed otherwise. You make a change in the register, everything else gets changed. So this shortens the development cycle. And a lot of engineers get affected by this approach. That's where I said operational excellence for the whole team. The hardware, verification, firmware, device driver, software, tech pubs, everybody gets affected by it. So it really changes. So the iDesign spec tool that we have is like one tool for all the stack of things that you need to do. So generate any bus client at the very low level, at the hardware level. Then generate any bus topology. You can configure how you want to connect those things, how you want to put the hierarchy, where you're going to put the decoders, where the arbiters. Generate any register type or any access, any special behavior. Use system RDL, IP exact. Generate hardware application logic. So FSM, glue logic, data path, you can use that. Generate register map and register sequences. And basically from that, generate the API for the hardware, which is used to generate the device driver. So creating that device driver, it takes, you capture it in one place and then, everything kind of falls out. Of course, these are building blocks. It's not going to create everything for all the details of the device driver, but it gives you the building blocks for creating the device driver. And so our iDesign spec flow is basically, either system RDL or PSS, so different ways of entering things. And from that iDesign spec, you generate a lot of things that are needed for your entire process. Thank you.